Everybody to this week's HAY seminar, and our speaker today is should be familiar to everybody here, but still, let me briefly introduce Kapusta, professor at University of Minnesota. There, he got his PhD in 1978 from UC Berkeley, and then he became a faculty in 1982 in University of Minnesota and stayed there since then. So today, Joe is going to talk about his new paper on the archive, just appeared like a month ago, I think, less than a month ago. He's going to talk about a neutron star with a crossover equation of state. Please go ahead, take it away, Joe.
Okay, so I can share screen, yes.
Yes, please, so. Yeah.
Let's see. There we go.
You have to, okay, great. Works now.
Oops. Okay, I have to put myself aside a little bit. Okay, so this is, as Xinyan said, this is some recent work I've done with one of my graduate students, Tom Welly, and I'm very happy to tell you about it this afternoon. So just a very quick introduction to show what sort of scales we're talking about. Ordinary matter is 1 to 10 grams per cc. Core density of the sun is 150 grams per cc, which actually isn't all that much compared to ordinary matter. Density of the atomic nucleus, 2 times 10 to the 14th grams per cc, and that's a number that we usually use to the funding agencies to impress them with how dense matter is. But in more natural units, it's about 0.15 nucleons per cubic Fermi or 0.14 GeV per cubic Fermi. Core density of a neutron star is about 1 GeV per cubic Fermi. That's about the same density the universe was 1 microsecond after the Big Bang, when quarks and gluons coalesced into hadrons. Densities achieved at RHIC and LHC are a little bit uncertain. It depends more precisely on how you interpret the data and where you begin, for example, hydrodynamic evolution. But that's much, much higher, 50 to 150 GeV per cubic Fermi. But of course, the baryon densities there are the entropy per baryon is much, much higher than in neutron stars. So I like to show this slide, Madhapa, Prakash. This is from Physics Reports 2007, and it showed an assembly of neutron star masses. Now it's almost impossible, or maybe it is impossible to know the mass of a neutron star unless it's in a binary system. So from top to bottom, you see neutron stars that are in X-ray or optical binaries. You see double neutron star binaries. You see white dwarf neutron star binaries, and you see main sequence neutron star binaries. Up until that time, there's a red vertical line drawn that indicates, well, it appeared that neutron star masses were limited to maybe 1.75 or 1.8 solar masses. There were a few outliers that you see in the green and the orange, but they have very big error bars. There was one star J0751. It was originally reported to be 2.2 solar masses, but it turned out that there was some instrumental problems, false signals, and that turned out to be a mass of about 1.3 solar masses. This plot was updated, you see at the very top, November 2010. And the reason for that is if you look down at the white dwarf neutron star binaries, let's see, my pointer, oops. Forget the pointer. There is one neutron star with a mass of 2 solar masses with very, very small error bars. And that's primarily the reason this plot was updated. So where did that star come from? That was a very famous discovery paper by De Morest and collaborators with the title "A 2 solar mass neutron star measured using Shapiro delay. This was published in Nature in October of 2010. So this is something that we lecture about when we teach general relativity to our graduate students. Here we have a pulsar, and it has a companion, which in this case turns out to be probably a white dwarf. This pulsar is 3.15 millisecond period. The orbit is almost exactly within the plane with the Earth. So we're looking almost edge on. In fact, the view is 89.17 degrees. And so as this companion star goes around the pulsar, or around their common center of mass, there is an effect due to general relativity, the distortion of space as signals come out from the pulsar and pass by onto Earth. Those are delayed a little bit. And there's a very standard theory for that. And here is a graph from their paper, which I don't know how it got published because there are no units on it. But anyway, there are the data points in red. It's a cycle after cycle after cycle measurements, and it shows the size of the error bars and a fitting of the curve. It also shows where the companion star is compared to Earth at each point on this plot. So in the middle where the peak is, the companion star is in the line of sight between us and the pulsar. And then as the white dwarf goes around, curve goes down and it comes up again. Oops. So what do they get from that? Well, they plot on the left shows the inclination angle versus the companion mass in units of the solar mass. Probability density on the right as a function of the polar mass, solar pulsar mass. And this was originally reported to be 1.97 plus minus 0.04 solar masses, which showed the very, very small error bars on that previous plot from Prakash. But since then, it's been updated because they've been observing it continuously. And it's now updated to 1.928 plus or minus 0.017 solar masses. That was a great discovery. But soon after, another 2 solar mass neutron star was discovered. And this was reported in Science in 2013. This is a 2.01 plus minus 0.04 solar mass neutron star orbited by a white dwarf with only 0.172 solar masses. Period is about 2.46 hours. And yet another, I mean, this is amazing. And this discovery was reported in 2019, I think, but published in Nature Astronomy in 2020. And this one shows 2.14 plus minus 0.1 solar mass neutron star. So we have at least, well, 2 neutron stars that are 2 to 2.1 solar masses and one which is very close to it. So the question is, what holds a neutron star up against gravitational collapse? Why doesn't it collapse into a black hole? Well, we all know the answer. The answer is pressure. Okay, where does the pressure come from? Pressure comes from an equation of state. So people say it's essentially held up against gravitational collapse because of Fermi pressure from the neutrons. Well, that's not entirely correct interpretation, but let's look at the properties of the nuclear force in atomic nuclei, just to refresh ourselves. So there's a long range attraction from single or correlated 2-pion exchange. So the ranges are about 1.4 Fermis for 1-pion exchange, half that for 2-pion exchange. But if that was all there was to it, then nuclear matter would collapse. And of course it doesn't, because we exist. That's proof of it. Short-range repulsion from vector meson exchange gives a hardcore or fairly hardcore potential of about 1/4 of a Fermi. So as I learned when I was a graduate student at Berkeley from my advisor and other people, the density of saturated nuclear matter is about 0.15 nucleons per cubic Fermi. Binding energy is about 16 MeV. There's something called Landau mass, which is about 83% of the vacuum nucleon mass. There's the compressibility. How compressible is nuclear matter? It's been a topic of investigation for a very long time. Let's just take it to be 250 MeV, not worrying about the uncertainties on that number. And then there's an asymmetry coefficient of about 32 MeV, which tells us that if you have more neutrons than protons, you have to pay a price for that. And that's the asymmetry energy. And there are one or two other parameters, but these are the main ones that I have in mind. So usually what one does for an equation of state is you can start out with neutrons, and then of course neutrons will decay unless they're polyblocks. So you also have to have protons and the electrons all in beta equilibrium. But once the matter is dense enough, you have to include 2, 3, and even 4 body forces in order to reproduce the known properties of nuclear matter near saturation density. Now, as the density goes up, chemical potential goes up, and once the chemical potential becomes high enough, exceeds the mass of a hyperon in nuclear matter, well, the hyperon can be formed. And so they will be formed due to electroweak interactions. People also allow for the possibility of transition to weakly interacting quark matter, possibility for transition to pion condensation, KN condensation, and those are the main exotica that people have considered. So that's all fine. Many people have constructed equations of state. The problem is that when you add degrees of freedom, that generally softens the equation of state. So what it means to soften the equation of state is that if you fix the energy density, the pressure goes down. That's what softening means. Fix energy density, pressure goes down. Why is that? It's because once you reach the threshold for producing a heavy baryon, you put energy into the mass of that baryon. And that means there's less energy going into fermion momentum for the remaining baryons. And that lowers the pressure, lowers it compared to what it would have been without the hyperon or hyperons. So I don't have many equations, but I show this one. This is a typical example of how people extrapolate from nuclear matter to very high baryon densities. It's Lagrangian, and it includes baryons, psi, includes mesons, sigma meson for scalar particle for attraction, the omega and rho mesons for repulsion. There's also a phi meson, which provides additional repulsion, especially for the hyperons. And you include as many hyperons as you like, and number of parameters there that need to be fixed. Now, the advantage of doing relativistic mean field approximation is that it's rather straightforward, number one. Number two, it guarantees that you do not have an equation of state where the speed of sound exceeds the speed of light. And that typically happens at high densities with non-relativistic potential type models. So if you want to make sure everything is in equilibrium, you have a few basic chemical potentials for baryon number and electric charge. So for example, the proton chemical potential is equal to the neutron chemical potential minus the electron chemical potential. Chemical potential for the sigma zero hyperon is equal to the neutron chemical potential, et cetera, et cetera. Put all these together. And when the chemical potential becomes large enough that you can have a non-zero fermion momentum, then interactions will produce those hyperons. They will convert protons or neutrons into hyperons. You also have to make sure that the system is electrically neutral, because neutron star cannot survive any significant electric charge. In the relativistic mean field approximation, the masses in the matter acquire effective values. For example, if m sub j is the vacuum mass of a baryon, proton, neutron, lambda, whatever, its mass in the matter is generally reduced by a coupling constant, g sigma j, times the average sigma meson field. Similarly, the chemical potentials acquire effective values. The true chemical potentials are what they are, but when you write down the field equations and mean field approximation, they look like independent particles moving with effective masses and effective chemical potentials. So many people have constructed such equations of state. So I take an old example from one of the books on my shelf. And this shows the pressure versus the energy density. And so first of all, you can start out with free nucleons. Free nucleons means neutrons plus protons plus electrons. And that's the dashed line. When you include interactions among the nucleons, the vector repulsion increases the pressure. And that's quite noticeable once you get above saturation density of nuclear matter, which I've indicated there with the green arrow. So that contribution of the pressure from repulsive forces in the relativistic mean field approximation eventually dominates the Fermi pressure. So interacting nucleons, that's a solid curve, and then it goes off continuously as the dash curve. And then once you include hyperons, once the energy density is high enough, chemical potential becomes high enough, you start producing hyperons. And as I argued earlier, once you produce hyperons, that softens the equation of state because you're putting energy into a mass rather than into Fermi momentum. And that reduces the pressure to what it would have been otherwise. So you can take these equations of state and you can calculate the mass of a neutron star as a function of the central energy density. And so it's been known since, I don't know, the 1940s, 1950s that free nucleons can produce a neutron star of only about 0.7 solar masses. And once pulsars were discovered in binary systems, it was realized, okay, free nucleons cannot reproduce their mass. If you include interacting nucleons only, pressure is much higher because of repulsive interactions, and with the coupling constants that are used here, you can produce neutron stars with more than 2 solar masses. But once you allow hyperons to enter the picture with reasonable values of the coupling constants, at least as was known in those days, that reduces the upper mass to about 1.5, 1.6 solar masses. And as we've learned in the last decade or so, neutron stars exist with much higher masses than that. So that's been the hyperon problem for the last 10 years. Just to see what sort of abundances you have, here's a plot of the baryon fraction as a function of the baryon density in those stars. So at low enough density, it's almost all neutrons with a small admixture of protons plus electrons that are not shown. And then actually the first hyperon that shows up with this set of coupling constants is the cascade. And then the sigma comes, and then the lambda, and a number of other charge states of these hyperons. And once you get above, well, you get to about 1.5 baryons per cubic Fermi, you have approximately equal numbers of all these baryons. So going back even further, paper that John Ellis and Keith Olive and I wrote 30 years ago, we considered what happened if you have a transition to quark matter at 4 times nuclear matter density. So we, again, did nuclear matter calculation with various types of hyperons. And here's a curve, it's called 0.485x. That just indicates that the phi meson is included for vector repulsion. And it's using a quark matter equation of state, which is just free quarks, up, down, and strange massless quarks. Alpha S is equal to 0. This was in the old days, so we used a compressibility of 300 MeV instead of 250. But you can see what happens if you have a first order phase transition. As soon as that phase transition happens, the star collapses into a black hole. We also allowed for the possibility of a second order phase transition at the same density, That softens the equation of state, and it reduces the mass, but it's not a whole lot of difference in the absence of quark matter entering via second order phase transition. So this is a plot of from the De Morest paper, and it shows the mass of a star as a function of radius for a large number of proposed equations of state. So the curves that are blue, these are for nucleons only. And as I showed earlier, if you have interacting nucleons, you can produce a fairly heavy neutron star. The pink shows nucleons plus exotica. And exotica could mean including hyperons. It can mean including a phase transition to quark matter. It can mean pion condensation, kaon condensation. And as I mentioned earlier, once you include other degrees of freedom, the pressure goes down at the same energy density, and that gives you a maximum mass star, which is lower. The green shows neutron stars made of quark matter only, strange quark matter. And as you probably read in recent months, NICER has provided us some information on estimates of the radii of several neutron stars along with their masses. And for some reason, when I read about those, the NICER results, the journalists talk about diameters instead of radii. So they give diameters of 24 to 27 kilometers. So those are certainly inconsistent with any sort of strange quark matter. The question is, for equations of state that have nucleons only, where are the hyperons? Why don't hyperons enter? Oftentimes, people just say we don't allow them. Other times, you can add extra terms beyond the ones that I showed earlier that provide such repulsion to the hyperons that they actually don't enter. They're just prevented from entering by terms that are entered in the Lagrangian. So you might say, well, why don't we just use results from a lattice calculation of the equation of state? Well, as we all know, lattice QCD is very good these days at calculating properties at finite temperature, but they cannot do zero temperature and finite chemical potential, not to any reasonable degree. But let's look at what lattice QC does show us at finite temperature. So here I show a plot of the pressure as divided by temperature to the fourth power, as is usually done. And the graph on the left shows P over T to the fourth as a function of temperature for zero chemical potential. So it shows a rapid crossover. It's not a phase transition, that's for sure. And so you might think, well, at low temperatures, the equation of state is dominated by a resonance gas. You have pions, protons, neutrons, rho mesons. Look in the particle data book, all the hadrons, put them in as non-interacting particles. And that generally describes the pressure for temperatures below about 100, 120 MeV. On the other hand, you know, at high enough temperatures, you have to go to quark-gluon plasma. Hopefully it's perturbative. We don't know that. If it does seem to be fairly strongly coupled, but let's suppose that it is. Perturbation theory can do a reasonable job, not perfect, but reasonable. And so we said, well, let's suppose that we have a switching function S, that carries us from the hadronic phase to the perturbative quark-gluon phase. So the switching function has to be a function of temperature. If you had a first order phase transition, you would have two phases in equilibrium at the same temperature, same pressure, but different energy densities. So then you would have something called F, for example. I wouldn't call it a switching, you could call it a switching function, but something F that tells you between those two energy densities, what fraction is quark-gluon plasma and what fraction is hadronic gas. So that happens at a fixed pressure and a fixed temperature, and then you just vary F. by hand. Here we're saying that the pressures don't have to be the same, and generally they're not at any temperature. So you provide a switching function. That switching function goes from 0 to 1. It goes to 0 at low temperatures and it goes to 1 at high temperatures. And the switching function has to be such that it's infinitely differentiable. You don't want to use a switching function that when you differentiate once or twice or even 3 times, that induces all by itself a phase transition. So we came up, actually Clint Young had the idea, come up with a switching function of this form, exponential of -1 over t to a power at 0 chemical potential. So I said, okay, well, what about finite chemical potentials? So we chose this sort of a switching function with the 2 parameters, the power n and the value t0. So then we just fit to the lattice data, and we fit to the 0 chemical potential data with those 2 parameters, as well as some parameters. You have to put some parameters into the perturbative QCD equation of state, because alpha s runs with temperature. You have to fix alpha s at some particular temperature. You have to prevent alpha s from diverging at some finite temperature. So anyway, T0 turns out to be somewhere on around 170 MeV, for example. Not surprising to anybody that's looked at lattice results or crossover. So that does a fairly good job of reproducing the lattice data. The dotted line indicates that the hadrons are treated as point particles. The other 2, excluded volume 1 and excluded volume 2, are 2 different ways of giving a finite size to the hadrons, saying once you have a hadron existing, another hadron cannot occupy the same location in space. So those are just 2 different ways of implementing an excluded volume, and it really doesn't matter which way you implement it. So I said, okay, well, they also have some data at finite chemical potential. So on the right, 400 MeV. So we said, well, we're not going to change the parameters. Let's just see how our parameterization does. Extrapolate finite chemical potential. And with no change in the parameters, we get a pretty good fit, especially using the excluded volume equation of state for hadrons. So then we also did what's called the interaction measure, energy density minus 3 times the pressure. If this was a gas of non-interacting massless particles, that quantity would be equal to 0, because epsilon is equal to 3p in 3 dimensions. So this is a measure of the interactions. And on the left is 0 chemical potential. On the right is chemical potential of 400 MeV. It's the same parameters we used in the previous plot, and does a pretty good job, especially with the excluded volume equation of state. So that was from a paper we published in 2014. And then the year later, we looked at some other quantities and decided to plot the square of the speed of sound. And again, no change in the parameters. These were fit simply by matching to the lattice results for the pressure and the interaction measure at 0 chemical potential. So you get a pretty good fit. The dashed line is for a gas of massless pions. So that's why it seems like it's kind of hooking down at low temperatures. That comes just from a non-interacting gas of free pions, and it has to be there. So you notice that the speed of sound is softened at a temperature of around 150 MeV, and that's because we're close to undergoing a phase transition. It's a rapid crossover. It's not a true phase transition, but it's close. If it was a true phase transition, the speed of sound would go to 0 for a first order phase transition. So then we said, well, we're motivated by these results. We say, well, can we do this at finite chemical potential, but 0 temperature? We said, okay, let's try it. So we said, let's take an equation of state where pressure is a function of mu only. And again, it's a switching function times the perturbative results plus 1 minus s times the hadronic results. And the switching function now, I should have mentioned the power that we used previously to match the lattice data was either 4 or 5. They gave comparable results. Now, I would say nowadays that 4 would be a better choice, because you want the pressure to be an even function of the chemical potential. And so if you put in the power 5 there instead, that's kind of strange. You'd have to put an absolute value over the chemical potential. And I'd rather not do that. So exponential of minus some parameter mu0 divided by mu to the 4th power. That's infinitely differentiable, will not give you a phase transition. So for the perturbative QCD results, we used some calculations done very long ago by Larry McLaren, his collaborator. So this is a perturbative QCD pressure. It's calculated to 3-loop order. We use a beta function that's calculated to 3-loop order. And we use 3 flavors of massless quarks. That's partly because the 3-loop calculation has not been done so far, to my knowledge, with massive quarks, first of all. Second of all, if all the quarks are taken to be massless, then you automatically have electrical neutrality. You don't need any electrons or muons. In any case, the strange quark mass is only about 100 MeV, and chemical potentials we're talking about are so high that you might as well take it to be massless. So there's only one new parameter that's going to be entered here, which is mu0. Because the hadronic equation of state, we're going to take from relativistic mean field theory. And for simplicity, we're going to use neutrons only. And using neutrons only means that we can provide just about the stiffest possible equation of state that you can, while being consistent with the known properties of nuclear matter. So the coupling constants that enter into the relativistic mean field theory were fit to the nuclear matter properties as they have been for decades. We imagine, as some people have published and talked about, that other terms are entered into the Lagrangian, and those terms essentially prevent any significant number of hyperons to be produced. So he said, let's keep it simple. We want to make a point. We don't want to make a claim that we have the most sophisticated equation of state. We just want to make a point about the crossover. So all parameters are fit except for mu0. We have an estimate for mu0 from fitting the lattice data and from physical arguments. Estimate was the mu0 should be on the order of 1.6, 1.7 GeV. And that, well, that comes out from T0 by, if you calculate the average energy or momentum of a massless quark or gluon, it's around 3 times T or pi times T. So you have to relate that to the average energy or momentum of a quark at 0 temperature, and how that's related to the chemical potential, and so on. So that's where the factor of 3 pi came from. So here's our equation of state, of pressure versus energy density. And we have considered, I'm showing plots for mu0 ranging from 1.8 to 2.4 GeV. So 1.8 or 2, I think, is about what we would have expected. 2.4 seems a little bit large, but okay, nature is what it is. So you can see at energy densities below about 500, 600, 700 MeV per cubic Fermi, it's essentially all hadron gas. And this is a log-log plot. So on a log-log plot, that slope is equal to, it's close to 1, because at high baryon densities and the relativistic mean field theories, the square of the speed of sound goes to 1. dp d epsilon is 1. Then once you have a crossover to quark matter essentially has a speed of sound squared of approximately 1/3. It gets corrected because of perturbative contributions to the pressure from the running coupling, but it's approximately 1/3. So you can see there's a crossover where the slope changes smoothly, goes from approximately 1 to approximately 1/3. So now let's plot the square of the speed of sound as a function of the energy density. So again, it's started low energy density, is rising rapidly. It wants to reach 1, but quark matter intervenes, crossover to quark matter. So for chemical potential mu0 of 1.8 GeV, crossover happens sooner. And so square of the speed of sound reaches a maximum value of about 0.3. and then it goes down a little bit, and asymptotically it would approach 1/3 at extremely high energy densities. If you increase mu0, that means the crossover occurs later at higher energy densities. So now the square of the speed of sound has a chance to increase before it reaches a maximum and goes down again. And finally, for the largest value of mu0 that we chose, 2.4 GeV, the square of the speed of sound reaches almost a half before it comes down and kind of levels off, and it's asymptotically, it's going to go up to 1/3. So this is behavior that is very similar to a plot that was speculated by Hughes, Carlson, Gandolfi, and Sanjay in 2018. They said, well, you know, we have hadronic matter, and if you want to make a very large, heavy neutron star, you need to have a stiff equation of state. So the speed of sound has to go up, and you know, if the higher it goes, the better. The stiffer the equation of state, and the more massive the star. On the other hand, we know that at large enough energy densities, hadrons just cannot exist. They overlap, and you have to have quark matter. So the square of the speed of sound should come down, and the question was, well, does it approach 1/3 from above or 1/3 from below? It's also very similar to the calculations of quark ionic matter by Larry and Sanjay just a year or two ago. I won't say anything more about that, only to point out that their quark ionic matter actually has a second order phase transition, whereas this one is strictly speaking a crossover.
Joe,
yes.
What happens to the sound velocity if you go, continue to go low to low energy density? Is it continue to go to 0? Or?
Then you get in the regime of nuclear matter.
Yeah, it cannot be 0, right? So, it cannot be 0.
Isn't it 0 at saturation density? I'm sorry,
not in neutron star matter.
Not in neutron star matter, no. But for symmetric.
Bound, but it's a very small value.
Yeah.
0 is only a 0 density.
Yeah, sure.
Yeah, and so I should also point out that we were not careful about, let's say, using an equation of state that's accurate below nuclear matter density. So if you're, in the crust of the star, our equation of state is not very good there. But this is a first study. We did not put in those kind of details.
That reflects in your mass versus radius curves, as you will show later.
Yes, so here is the mass as a function of central energy density. And so for the 4 chosen values of mu sub 0. So for mu sub 0 of 1.8 GeV, we chose that one as the smallest because that gives a maximum mass of 2.01 solar masses. And then we incremented by 200 MeV until we got to 2.4, and that gave a 2.2 solar mass star. Once you go above about 2.4 for that crossover parameter, there's no contribution from quark matter left in the neutron star to speak of. So it's just a pure neutron star. So there's no point in talking about a crossover. So that's what you see. Central energy densities at maximum mass are on the order of, well, somewhere between, say, 800 MeV per cubic Fermi and 1 GeV per cubic Fermi. So no big surprise there. Now you can do the mass radius relationship. So again, the same for crossover parameters. And what you see is those curves start to separate for mass of about 1.4, 1.5 solar masses. Radius there is about 13.4 kilometers. And then it bends around, as all reasonable equations of state do. And you reach a maximum mass, and the radius of the maximum mass is, somewhere could be 12 kilometers, it could be 12.5 kilometers, depending upon which of those crossover parameters you like. So going back to the nicer data, one neutron star that they had looked at was, correct me if I'm wrong, was 1.4 solar masses. And the diameter was quoted as somewhere between 25 and 27 kilometers. So you half that, and that's consistent with 13 point something. And then for a 2 solar mass star, or close to it, diameter was more like 24 to 26, 24 to 25. So that's, this is roughly consistent. I don't want to say that, this is the final equation of state. I just want to point out that this is one possible way to incorporate quark matter without having a phase transition. So you can also ask the question, how much quark matter is in the star? And that is not really a well-posed question, because if you ask how much of the baryon density is contributed by quarks versus hadrons. If you go back to the equation of state, remember the pressure as a function of mu involves a switching function times a pressure as a function of mu from each of the two phases. To get the baryon density, you have to differentiate that pressure. So the baryon density, normally you would say some fraction comes from quarks, some fraction comes from hadrons. But in this case, with a smooth crossover, the switching function itself contributes to what you mean by the baryon density. So the switching function is really telling you what fraction of the pressure is contributed by quarks. So the fraction of the pressure contributed by quark matter is shown here as a function of radius for the maximum mass star at each value of mu0. So if the crossover happens sooner at lower energy densities, for example, mu0 is 1.8 GeV, then about 10% of the pressure at the core of the star is contributed by quarks. On the other hand, if you delay the transition to crossover to quark matter by choosing mu0 to be 2.4 GeV, then only about 1% of the pressure at the core is produced by or contributed by the quarks. So that is how you might interpret the contribution of the quarks, not by the fraction of baryons. So I might have gone a little fast, or maybe I did not have enough on my slides, but at this point, I can just give you the summary. And the summary is that we studied the masses, radii, central energy densities of neutron stars using an equation of state that has a smooth crossover from hadronic matter to quark matter. This is motivated by the lattice QCD calculations at finite temperature with zero chemical potential or small chemical potentials. Those up to the chemical potentials that have been used so far, lattice results indicate no phase transition, but it might still happen. There might still be a critical point. We said, well, let's suppose there is no critical point. Let's suppose it's a smooth crossover all the way down to zero temperature. Now, this approach is very flexible because we put in an hadronic equation of state. We put in a perturbative QCD equation of state, and then we had a crossover function. You can use that same crossover function with your value of mu0, whatever you want it to be, put in your favorite hadronic equation of state, put in your favorite quark matter equation of state, and redo the calculations. Put in a better part of the equation of state that's relevant to the crust than we did. So I view this more as a philosophical approach or calculational approach, not as a definitive equation of state. The hard work really comes in calculating the two different phases. Now, what observational effects might support the crossover equation of state rather than no quark matter at all, or a first or second order phase transition? I don't know, apart from the maximum mass that's allowed by a particular equation of state and the mass versus radius relationship. So I want to thank you all for coming, and I'm happy to entertain questions.
Well, thank you, Joe. As always, very clear talk. I always enjoy your talk. You make things so simple. We can have questions, answers now. And if you want, please raise your hand.
Oh, just speak.
Yeah, I'll just speak.
I'm not very good at looking and raising hands.
Yeah, Jennifer, please go ahead.
Hi, thank you. That was a wonderful talk. I have a question back on your strong Lagrangian. When you were showing the terms that corresponded to, I think it was the vector mesons.
Yes.
So the repulsive term, tell me, is that the -1/4 phi mu nu, phi mu nu? Where is the repulsive vector meson interaction? Or am I...
So the repulsive part comes from the next one, the 1/2 m phi squared, phi mu.
The mass term. Oh.
Yes, yeah, because the it's sort of analogous to QED or electromagnetism, that the average value of the field is the time component, phi 0.
Yes.
Or omega 0, for example, is proportional to the baryon density. So you can think of the time component of phi 0 or omega 0 as being proportional to density. So then you get density squared.
Yes.
And so maybe I should have put a couple more equations in my talk to show that the pressure actually is proportional to density squared at high density.
And Joe, does your answer tell me, so my second question, which you might have just answered, is why is the vector meson, that short range repulsion, why is that not sufficient to hold the star up?
Well, I mean, there's the speed of sound is limited by the speed of light. And so the pressure can only rise so fast. And that ultimately provides a maximum mass for the star. So if you can have other contributions to the Lagrangian, other equations of state that are stiffer in the sense, for a given energy density, the pressure is higher and essentially the speed of sound is greater at that energy density, but it's limited by special relativity. You can't have a speed of sound bigger than 1. So that's, and Madhapa Prakash has written papers on this and trying to extrapolate from known properties of nuclear and neutron matter and saying what's the maximum mass allowed by special relativity. And he would be a better person to address that question than me.
Very good, thank you. I'll read his papers.
Joe,
the next one, Agnieszka.
Hi, thank you for a very nice talk. I would like to ask you about this baryon density that you get from the pressure with a switching function. You said that it's a little bit ill-imposed question to ask how much quarks you have or how much hadrons. And I am wondering if this means that is your model still thermodynamically consistent if you cannot ask this question anymore?
Oh, it absolutely is. So the natural variables for the pressure are mu and T. And so that's why all along we've been expressing pressure as a function of mu and T. In this case, T is 0, so it's just mu. So the two phases have the same chemical potential. The pressures are not the same. If the pressures were same at the same chemical potential, you might say, well, there's a phase transition there. But we don't require the pressures to be the same anywhere. It's just a crossover. But the two phases do have the same chemical potential. So it's consistent.
I see. So also just a follow-up. Because of this, I think at least, because of this form of the baryon density that you get, you will also have such mixed term in the energy density, I believe. And
yes,
that you say is also not a problem, really.
That's not a problem. It's all thermodynamically consistent. Yep.
Okay, thank you. Thank you very much.
It does look peculiar, and we've thought about it. That looks peculiar, but that's it. That's what happens when you have a crossover.
All right. Well, if it hangs together, it hangs together. Thank you.
Prakash.
Yeah, I have a couple of comments and questions. Maybe Joe can react to that. The comments are, this looks, the switching function that you talk about looks very much like what I would get if I were to do Gibbs constructions, a la Glendenning.
Right.
This
Yes.
particular company. Except there is a kink at exactly the point, but a zero weight at any, it doesn't matter much. So it looks very much like that. And Sophia and I, and with my graduate students and Latimer wrote a big paper on that, treating quarks in within neutron stars. And we explored the consequences of what McLaren and Reddy did, Sanjay did.
Yeah, their equation of state is actually second order phase transition.
Correct.
Yep.
Correct. But it has sort of, not too many consequences for the mass and radius.
Well, if I may interrupt you, and I will keep your questions. Here is the calculation we did if the phase transition was taken to be second order. So we make it second order by adding a term on the quark side, which is proportional to mu squared and a constant. So then there are two extra parameters. And so we adjust those parameters by saying, we want a phase transition at this value of the chemical potential. And so we have to match the pressures and we have to match the baryon densities. Okay. And that gives you a second order. So on the left is the square of the speed of sound, and you can see it goes up and then just sharp.
Fantastic. Sorry, what is this? Exactly... This is some new equation of state you put in?
No, it's the same hadronic equation of state and the same quark-gluon equation of state, except on the quark-gluon side, we added a constant plus another constant times mu squared.
Oh, I see.
So that's what John Ellis and Keith Olive and I did way back in '91.
Okay, this looks exactly in reverse to what Jim Latimer and Zhao, his graduate student, show in their graph. So I'm sort of pleased to see this. So
that's what happens with a second order transition.
Yes, so I should understand that in more detail. Now, the reason why you got such peculiar looking mass radius curves was because you essentially did not pay too much attention to the very low density equation of state.
So that's this one. Yes, at the low density equation of state, near the crust and below nuclear matter density, this is, it's not reliable.
Okay, and I'll send you the equation of state in a tabular form, so you can use it.
Yeah. So Tom made the graph, and I said, well, it looks. He said qualitatively it looks like other people's graphs. And I said, well, it's not quantitatively accurate, but he said let's show it anyway, so we show it.
Sure. The question I have with respect to this graph is, let's look at the radius of a 1.4 solar mass star. Right. That's in excess of 13 kilometers. And that at the maximum mass star, that's about 12 kilometers. Now, the big question is whether the radius of a maximum mass star and that of a 1.4 solar mass star are the same or different, and if different, towards the positive side or towards the negative side. NICER seems to indicate nearly the same mass.
With big error bars.
With huge error bars.
Yeah.
And so this is an open question as of now. So what is your take on this?
I think these results look reasonable, but again, put in your favorite hadronic equation of state. The quark matter equation of state is, I think it's fairly reliable because it's a 3-loop calculation. So it's on the hadronic side that really needs, put in your favorite one. We just wanted to write a short letter. We didn't to put this out there for a crossover. This is how you would do a crossover.
Okay, fair enough. Now, I was quite intrigued by the role that you emphasized on how the switching function itself lends things that you don't anticipate usually. I mean, I had not anticipated that from my Gibbs crossover, right?
Right.
It's not a crossover, Gibbs just dilutes things. So can you expand a little on that? Why the switching function does all that? Because is it because simply it's a function of temperature or a density on its own?
Well, as was asked earlier, that form for the pressure with that switching function, when you do it that way, it's thermodynamically self-consistent. So at a given chemical potential, part of the pressure is contributed by quarks and part is contributed by hadrons. But because of that form of the switching function, you can't say it's the same fraction of baryon number. And that is a little bit peculiar, but I mean, there's nothing thermodynamically wrong with it.
Yeah, I see that, but it's intriguing.
Yeah.
Okay, we have a question from No.
Hi, Joe. Thank you.
Hello.
I have a question, maybe just for my education. You had a plot the mass, solar mass as function of energy density. When you include the hyperons, you say that the mass dropped to 1.5 solar mass.
This one?
My question is, those hyperons, are they interacting or non-interacting?
They're interacting. And so the notation, the notation here, 0.48 indicates a parameter in the interactions, and the phi indicates that the phi meson is included in the X. I forget what it means, but no, they're interacting with the Lagrangian that I had showed.
This is plot of density. You had one with energy density.
Energy density. This one?
Next, the one after that.
This one?
Right. Yes.
Okay.
But I thought we do not really know. We don't have much information about the nucleon-hyperon interaction. Do we?
There's not much. As you know, there's some information coming from heavy ion collisions from HBT, which tells us a little bit something about the hyperon-hyperon interaction.
Yes,
low
that's
energy
what we are
hyperon.
trying. That's
Yeah.
what we are trying.
Now there's a very nice paper by Schaffner-Bielich and his collaborators, which is cited in our paper, where they go through a model which includes the baryon octet and I think the decaplet, and they have several parameters that relate all the coupling constants, and they calculate neutron star masses, and you can make the equation of state stiffer or softer by varying these different parameters. I think if you look at the paper, I think they're called alpha with some subscript. These hyperon, the coupling constants enter here, hyperon or hyperon nucleon coupling constants. They're taken from some older work on the binding of hyperons and nuclei. Horst Stucker and other people extracted those numbers quite some time ago.
All right, thank you.
Joe, on this plot, this is the softening of the equation state by hyperon is only for the hadronic matter, right? As soon as you introduce Quark's degree freedom, the hyperon does not really do that much anymore, right?
No, the hyperons would still soften the equation of state. How much quantitatively?
How much quantitatively? For example, in your current crossover, you can still add on. You can still add like hyperon in your hadron gas equation state. But as soon as you cross over, it does not really do much anymore, right?
Which plot do I want to look at? I'm not sure. Well, we could look at this one. So this is, this tells you the fraction of the pressure contributed by quark matter at the core, which of the heaviest star. So that's the extreme limit, and you can see here that it's still not very much. 1% to 10%. So if you soften, I'm not sure which one to look at.
10%, you soften it, it probably does not really do that much. Right?
Not much.
Yeah.
So that's why we we assumed that the coupling constants were such that hyperons are highly suppressed.
I see.
And so just ignore them, just for a proof of principle that you can do this crossover and what happens.
It's interesting. Your velocity of sound can go almost as high as like 5.6, and this is of course this is speculated by many people from the recent gravitational wave experiments. Okay, well, thank you so much. Are there any other questions? Yes, Jennifer, yeah, the last one.
Oh, thank you. So I have a question about adding degrees of freedom and removing degrees of freedom. So if you had something, this is completely out there, I'm sure it's not there, but like a 6-quark dark matter object that's effectively taking 2 neutrons or a neutron and a proton and combining them into a single object, would that, if it happened, would that be removing a degree of freedom and therefore changing the equation of state in a more positive way?
I have to think about that. I don't know, Prakash, maybe you have intuition at the moment. My guess is if you combine 2 baryons into one with roughly double the mass, that would lower the pressure.
The simple answer is unless interactions play funny games, adding more degrees of freedom always reduces the pressure at the same density, baryon density. But as Joe points out, asking the question about baryon density alone is not quite kosher. You have to work with other variables.
Well, energy density.
Energy density is a good variable. Yeah. So that would be my guess. But guesses are guesses. I mean, you have to actually do the calculation to see what they say, and then learn from it, right?
It should be a relatively straightforward calculation for non-interacting particles. Just
that's right.
Convert some of them.
It's usually the interactions that play the havoc. And
but I think the 6-quark dark matter is actually a strongly bound 6-quark object. You mean interactions with other stuff? Sorry.
Well, interactions between themselves and other stuff, right? I mean, just as in the case of hyperons, hyperon-nucleon interactions were not so much paid attention to before. Many people did. Hyperon-hyperon interactions were not paid much attention before, so many people did. So the picture changed, right? So you live and learn in some sense.
So let me rephrase that. Okay, think of this. You have 2 baryons and they get too close together. There's a strong repulsion between them. That raises the pressure. But now if you say there's an attraction, a short range attraction between them, so they actually merge into one with baryon number 2 instead of 1, that repulsive energy is gone. So I would think that this would reduce the pressure. But it should be a straightforward calculation. A homework problem.
Thank you.
Okay, with that, let's thank you again for this wonderful talk, and also for your time to talk to us.
I wish I was there so that you could take me out to dinner.
Yeah, definitely.
That would be great.
And then come here, please. Please.
We will definitely take you out to Jupiter. We definitely need some cup of beer afterwards.
Yes.
Joe.
Hi.
Ellen is waiting for the cocktail.